every textbook you've ever read in every subject throughout the 12 years from elementary school all the way to high school. That's a lot of reading, right? Now imagine if an AI could gulp down all of that in one go. Sounds like sci-fi? Not anymore. Today, we're diving into MiniMax-01, a cutting-edge AI model that's going toe-to-toe with state-of-the-art models like GPT-4o and Claude-3.5-Sonnet. But what sets it apart is its context window, 20 to 32 times longer than its peers, with a staggering capacity of 4 million tokens. The secret is in a technique called lightning attention. It uses a clever tiling method to split computations into intrablock and interblock components, achieving linear complexity and tackling inefficiencies in causal language modeling. So, buckle up. This is going to be an exciting journey. Let's get started.
The MiniMax-01 series are a groundbreaking set of models designed to push the boundaries of what's possible with large language and vision language systems. These models, MiniMax-01 and MiniMax-VL01, are built to compete with heavyweights like GPT-4 and Claude-3.5-Sonnet, but with a unique twist. They can handle much longer contexts. How? The secret sauce is something called lightning attention, which makes these models incredibly efficient. Now, these models are massive. 456 billion parameters, massive. But only 45.9 billion parameters are activated per token. This is thanks to a mixture of expert strategy, which we'll get into later. Training these models is also super efficient because of an optimized approach that overlaps computation and communication. For example, MiniMax-TextOps1 can train with context windows up to 1 million tokens and scale to 4 million tokens during inference. That's a big deal when you consider the usual memory and compute constraints. On benchmarks, these models are no slouch. They perform on par with the best models out there while offering 20 to 32 times longer context windows. And MiniMax-VL01? It's a beast in multimodal tasks, trained on 512 billion vision language tokens. Take a look at the figures here. You'll see MiniMax-01 outperforming many state-of-the-art systems, especially on long context tasks like ruler. Let's get into the introduction now. Large language models and their vision language cousins have made huge leaps in tasks like answering complex questions, understanding code, and reasoning. But the context windows they handle are usually capped at around 256,000 tokens. That's often not enough for real-world situations, like analyzing entire books or managing large-scale programming projects. Why is this a problem? Because the transformer architecture scales quadratically as context length increases. That makes the computational cost grow faster than hardware can handle. People have tried solutions like sparse or linear attention, as well as state space models, but these often don't scale well in practice. So here's the main idea. The paper introduces a hybrid architecture with lightning attention to keep computations efficient. They also enforce a practical constraint, handling over 1 million tokens using just 8 GPUs. On top of that, they use a mixture of experts approach, where only part of the model's parameters activate at once. They also use advanced parallelization techniques. This setup keeps the model running efficiently, even with billions of parameters and context windows extending to millions of tokens. Now, how were MiniMax-TeX-01 and MiniMax-VL01 trained and evaluated? They started with a diverse, high-quality dataset. They improved data quality with reward-based techniques and balanced the data to cover various tasks well. A 3-stage training approach extended MiniMax-TeX-1's context window to 1 million tokens, preparing it for long context scenarios. MiniMax-VL01, meanwhile, got a lightweight vision transformer added to handle images in addition to text. It went through a 4-stage process trained on 512 billion vision language tokens. Want to see the results? Look at Figure 2 here. You'll notice they match or exceed the performance of closed-source models on standard benchmarks. And for contexts over 200,000 tokens, MiniMax-TeX-1 pulls ahead of competitors. Figure 2 also showcases its latency benefits, demonstrating how effectively the architecture scales. Let's look under the hood of MiniMax-TeX-1's architecture. It's built around a transformer-style block with 2 major components: channel mixers, for attention, and feature mixers, driven by a mixture of experts, or MOE system. To enhance efficiency, it alternates between linear and classic softmax attention. A load balancing strategy, taking cues from G-shard, keeps the MOE blocks stable. Deep norm further stabilizes training across many layers. The pattern is, for every 7 layers of linear attention, there's one softmax attention layer. Each layer has 64 attention heads, each with its own embedding size. They also incorporate group query attention, GQA, for parameter sharing and rotary position embeddings for improved sequence encoding. The final model has 80 attention layers, weighing in at 456 billion parameters total. Only 45.9 billion of them are active per token because of the MOE setup. Look at Figure 3 to visualize this structure. You'll see how MOE substitutes the usual dense feed-forward networks, scaling better for massive tasks. Next, let's talk more about the Mixture of Experts (MOE) framework in MiniMax-01. The MOE is made of multiple expert networks, each handling a specific subset of tokens. A router decides which expert is best for each token, spreading the workload around. There's also a token drop strategy. Each expert has a token capacity. If it's full, extra tokens get discarded to keep things balanced. In Figure 4, you can compare an MOE model to a dense 7 billion parameter model on benchmarks like HelloSwag, Wino Grande, and Trivia QA. Under the same compute budget, MOE scores better. There's a challenge called routing collapse, where one expert can end up doing too much work. To avoid that, they add an auxiliary loss to keep tokens evenly distributed. A global router also coordinates token distribution across GPUs, cutting down on imbalances. This approach keeps the model scaling smoothly. Now, onto linear attention and the upgrades that make it efficient. Traditional attention has a quadratic cost because it has to handle interactions across all token pairs. Linear attention reduces that cost by focusing on a more compact matrix product. Softmax attention typically multiplies large matrices over and over, which grows quickly with sequence length. Linear attention sidesteps much of that overhead. Look at Figure 5 to see the contrast. Softmax attention does multiple large operations, whereas linear attention only does a small set of matrix products. This is why linear attention stays efficient for longer sequences. That said, there's a known limitation in causal tasks, where cumulative sum steps reduce parallel efficiency. This is where lightning attention comes into play. It's an optimized implementation that eliminates these bottlenecks. It smooths out large-scale language modeling tasks, where older linear attention methods sometimes stumble. Lightning attention addresses a big efficiency problem by splitting the attention calculation into intrablock and interblock steps. The intrablock part handles local computations. The interblock part combines those local outputs on a broader scale. This keeps the overall complexity linear, even for very long sequences. Mathematically, the method partitions key matrices into smaller blocks, which compute their local interactions, intrablock, and interactions across blocks, interblock. By breaking it down like this, there's no need to repeat big sums over and over. If you look at the diagrams here, you'll see how these blocks work recursively. They reduce unnecessary computations, especially when sequences get extremely long. It's a modular setup that maintains speed and scales effectively. Continuing with lightning attention, there's a block-based forward pass algorithm that partitions the query, key, and value matrices into smaller blocks. Operations happen within and across these blocks, and the results get fed back for the next step. This approach holds the complexity steady at linear, even as sequence lengths increase. However, the text here also points out a limitation in smaller scale tests. Purely linear methods can struggle with retrieval tasks. That's why a hybrid approach mixes lightning attention and softmax attention. They alternate between them. There's a table you can check out here that compares the computational costs and parameter usage for different setups. Lightning uses fewer resources, while softmax has better retrieval. The hybrid version balances both for larger scale settings, tested in model sizes from 70 million to 7 billion parameters. Up next, the discussion shifts to scaling laws for these attention mechanisms. The table shown here reveals how these models scale with respect to model size, dataset size, and available compute. We see that hybrid models bring together the strengths of both softmax and lightning attention. They manage to achieve lower training loss while using more parameters and tokens. Look at the 3 plots. They show how loss, model size, and token count vary under different compute budgets. Softmax is good when you're small scale, but once the model and dataset grow, lightning and hybrid approaches catch up or surpass it. The training setup is consistent across these experiments. A batch size of 4 million tokens and an adaptive learning rate. Benchmarks like BoolQ and OpenBook QA were used, and the hybrid models stand out in handling large data. Overall, multi-mechanism integration seems to pay off for big tasks. Now check out Figure 7. It compares different attention types on various benchmarks, common sense reasoning, retrieval, and more. Hybrid lightning consistently does well. Pure lightning is solid overall, but can lag in retrieval tasks like NIAH. Hybrid lightning also stays on par with softmax in adaptability. That makes it good for in-context learning. Look at Figure 8 if you want to see training speed. The hybrid lightning model scales efficiently as sequence lengths go up, surpassing regular softmax-based approaches. Some other models, like HGRN2 and Mamba2, are shown for comparison. Lightning attention has steady throughput across large datasets, which is why it's a good candidate when you need speed and performance together. Next, there's a closer look at different hybrid architectures, like hybrid-Cosformer2 and hybrid-HGRN2. These combine linear and softmax layers in varying patterns. Table 3 shows that hybrid lightning emerges as a top performer across downstream tasks, such as NIAH and scrolls. It offers strong throughput without sacrificing accuracy. Then we see a mention of sliding window attention, a softmax-based method that uses window sizes to manage memory. Table 4 reveals hybrid lightning outperforms those window-based models in large tasks, especially on accuracy-sensitive benchmarks like NIAH. The main takeaway? Linear models alone are efficient, but can lack adaptability for some downstream tasks. Hybrid lightning finds a sweet spot where you get both performance and scalability. Here we learn how hybrid lightning excels in retrieval and extrapolation tasks. It can basically revisit large segments of input, somewhat like rereading chapters in a book. Linear attention models often can't do this effectively, so they miss out on retaining data from earlier in the sequence. Hybrid lightning's capacity helps it outperform softmax in certain tasks. We also see module ablation studies in the MOE framework. First, swapping out early layer softmax with lightning attention boosts accuracy. Second, the difference between pre-layer and post-layer normalization is tested. Post-layer normalization, applied after residual connections, proves better for stability and performance in deep stacks of layers. This part continues the discussion about training large language models. Different normalization methods can affect stability. Post-layer normalization helps avoid exploding or vanishing gradients. The experiments here confirm that it improves reasoning and math tasks. We also see details about the overall model specification, with a cap of 500 billion total parameters to keep single-device inference feasible. That means no cross-machine communication is needed. They also talk about balancing architectural choices, like the ratio of attention types, the depth versus width of the network, and how memory is allocated. In their findings, deeper models generally do better, and tuning attention memory dimensions can give a nice performance boost. Scaling laws reappear here, providing a blueprint for choosing optimal model sizes given activation parameters and token budgets. They even project these laws out to much bigger models. So the design picks a configuration with over 450 billion total parameters, aiming for a balance of accuracy and efficiency. They then pivot to computation optimization. 3 big challenges stand out: cutting down the communication overhead when training with many experts, distributing tokens across GPUs to handle massive context windows, and fine-tuning the lightning attention for real-world inference. Off-the-shelf frameworks don't do all this well, so they built a custom distributed training framework for higher efficiency. Here, the text explains how they manage expert configurations in large-scale models. There's a trade-off between memory usage and compute load when you compare tensor parallelism and pipeline parallelism. Tensor parallelism can be heavy on compute, while pipeline parallelism can eat up a lot of memory if context windows are very long. They propose a new partitioning approach with 2 process groups: expert tensor parallel and expert data parallel. The first spreads out weights among experts, while the second handles data parallelism for identical experts. An overlap strategy merges computation and communication, so GPUs are less idle. Figures show how this overlapping helps performance, but scaling the number of groups can complicate scheduling, so they aim to strike a balance there. Now we look at advanced optimization for very long context training. Different samples have different lengths, so if you pad them all to the same length, you waste a lot of compute. Their solution is data packing. Instead of padding, they line up sequences end-to-end along the sequence dimension. This cuts down on wasted space. They also mention Varlan ring attention, a technique that's built on a ring-based structure. It helps distribute data more effectively for scaling. They adapted it to address bottlenecks in existing approaches, meaning they can handle sequences up to 1 million tokens more efficiently. Varlan ring attention helps with variable length data. Traditional ring attention techniques often require fixed size padding, which can be inefficient. By applying a ring algorithm directly to these data-packed sequences, they reduce wasted padding even further. The figure here illustrates how they optimize both causal and non-causal computations. LASP, linear attention sequence parallelism, also comes up. LASP can slow down because it depends on sequential communication across different groups. LASP Plus fixes this by removing interdependencies, letting tasks run in parallel. That speeds things up for bigger sequences. Now we compare LASP and LASP Plus. LASP starts by splitting input sequences, then processes them step by step. Communication between ranks is still needed at each step, which reduces parallel performance. The figure here shows where the inefficiencies arise. LASP Plus tackles this problem by letting each rank compute a local prefix sum in parallel. Later, an all-gather operation merges the local results into a global prefix sum. This streamlined approach lowers the communication overhead and boosts speed. It's the same fundamental idea, but without the bottlenecks. In LASP Plus, all those serial dependencies are eliminated. Because every rank computes things in parallel, the entire operation scales well. Yes, there are extra memory and communication costs with the all-gather step, but the performance gains often justify it. Tests show big speedups, potentially proportional to the number of parallel nodes. They also discuss data packing more, aligning sequences by padding them to a block size, then concatenating them. That makes the GPU usage more uniform. For inference, they rely on 4 optimization strategies, such as kernel fusion and batched matrix ops, to keep real-world deployments running smoothly. Next, there are 3 main optimization strategies for lightning attention. First is batched kernel fusion, which merges multiple operations into one to save memory bandwidths. This can cut latency by up to 10%. Second is a separated prefill and decoding strategy. Sometimes you have tokens of length 1 mixed with tokens of larger lengths. Splitting them into 2 separate kernels reduces latency by about half. Finally, multi-level padding automatically adjusts the padding blocks to the input's actual size, preventing wasted compute. This helps a lot when dealing with multiple requests of different lengths at once. Now we move on to further optimizations and pre-training. Strided batched matrix multiplication is introduced, taking advantage of hardware accelerators. It feeds lightning attention's data more efficiently, boosting resource usage. The focus then shifts to the pre-training of MiniMax-01. They built a carefully curated dataset, drawing from academic literature, online sources, and more. The data goes through a rigorous evaluation pipeline to measure quality without draining too much compute. They also use a hierarchical training approach to scale the model's context length gradually from 1 million tokens to 4 million. This ensures strong performance without blowing up memory costs. Data quality is critical, so next they describe advanced filtering and deduplication. They evaluate data on knowledge depth, helpfulness, and relevance. When pulling text from websites or books, they format it carefully to keep it readable, but still logically consistent. They also tune how much of each data source goes into the final mixture. The tokenization strategy is byte level and has a vocabulary of 200,000 tokens. This compresses multilingual text effectively. They then run experiments to see how data quality and structure affect both model training and compute usage. It's all about striking the right balance. We hear about repeated data's effect on training. They use a statistical approach to compare different data setups, normalizing metrics to eliminate bias. Proper setup reduces data redundancy and makes evaluations more meaningful. Too much repeated data can hurt generalizations, especially if that data is lower quality. It can drag performance down. So they propose a deduplication method that lines up with the final training schedule. This ensures data stays fresh and doesn't get reused too often, preserving efficiency and performance gains. This section explains the training strategy for MiniMax-01 in detail. They start with a specialized parameter initialization that stabilizes training at the outset. The batch size is small at first, then grows over time, balancing efficiency with the risk of higher loss. There's a chart, check it out here, showing how training loss correlates with batch size under a power loss scaling. The learning rate warms up, peaks, and then adjusts gently. They also show how they systematically scale the context length from 1 million to 4 million tokens. They gradually upsample long context data so the model can handle it. They do this in stages to avoid distribution shifts, making sure short context evaluations still remain strong. They continue focusing on long context extension and their post-training framework. The needle in a haystack metric is explained, but they found it wasn't the best at reflecting overall progress. So they went for a more nuanced evaluation with increasing task complexity at different checkpoints. They also outline a data recipe for training long contexts by dividing data into short, medium, and long categories. For post-training, there's a big emphasis on safety and alignment. They build a high-quality dataset and use a layered reward system to measure truthfulness and helpfulness. Supervised fine-tuning plus reinforcement learning help the model remain robust, even with extended contexts. Now we get into how they collect prompts, build reward models, and do supervised fine-tuning. They gather a broad range of user queries, sorted by task type and difficulty, making sure to remove duplicates. Then the reward model scores responses for correctness, truthfulness, helpfulness, and harmlessness. Supervised fine-tuning uses expert-created datasets, guided by techniques like rejection sampling and diversity filters. This multi-stage process ensures the model can handle complex, real-world prompts accurately and responsibly. Reinforcement learning comes next. They discuss direct preference optimization in an offline setup, taking responses from the SFT-trained model and choosing the best ones for further training. This aligns the data distribution more closely with what users actually want. They also talk about online reinforcement learning. By revisiting prompts that had various success rates, the model keeps improving without overfitting. A new optimization method controls policy consistency by tweaking sampling weights and advantage estimations. Safety alignment is woven throughout to keep the model both helpful and harmless. We see even more strategies for safety, adaptability, and long context handling. The training data pipeline is carefully structured to be diverse and accurate, including real-world data and specialized safety prompts. Data augmentation expands coverage, so the model can handle tricky scenarios. A harmless reward model specifically balances safety with overall usefulness. For long context adaptation, they use a multi-stage plan. They start with short contexts, move on to longer contexts, and alternate preference optimization for both. This helps the model remain accurate when dealing with extended input while adhering to safety guidelines. Next, we get to benchmarking. They evaluate both short and long context tasks. The model demonstrates strong performance in broad knowledge areas, tricky reasoning problems, and math. It can handle graduate-level content, follow detailed instructions, and even tackle coding. They also highlight knowledge boundaries, math pass rates, and factual accuracy. Methods like zero-shot reasoning help it align responses with what humans expect. Comparing MiniMax-01 to other models shows that it balances performance and usability well. This is important for real-world application, where tasks range widely. In Table 8, you can see how MiniMax-01 stacks up on benchmarks around reasoning, math, and coding. It shows competitive or strong scores across the board, including factual tasks. For long context tests, they focus on memory and understanding across multiple rounds of dialogue. There's also a new multi-round needles in a haystack benchmark that checks whether the model can retrieve information effectively from large contexts. This helps prove it can handle extended inputs in practical situations. We continue with long context understanding and reasoning tasks. Datasets like Ruler and Longbench-V2 are used to test logical reasoning, multi-document analysis, and multi-turn dialogues. The results, displayed in graphs here, show that MiniMax-01 holds performance steady even as sequences grow longer. It sets top results for chain-of-thought reasoning and remains accurate in ultra-long contexts. The hybrid architecture and alignment techniques make it robust for these challenges, highlighting its potential in real-world scenarios that need extensive context. There's also an evaluation with MTOB, focusing on translating between English and Calamang, a low-resource language. The model learns from partial examples in a grammar book, then tries to translate queries. It surpasses prior benchmarks, scoring high on metrics like CHRF. This is impressive considering the pre-training corpus didn't have much Calamang data. It shows the model can adapt to new tasks with minimal guidance. Looking at the MTOB dataset again, the results improve further during long context training. Metrics like BLERT and CHRF confirm that. Although there's barely any Calamang data in pre-training, the model still does well. Then they switch to user-in-the-loop evaluations, featuring interactions from the Hailu AI system. These tasks cover coding, safety, and creative writing, often in Mandarin. MiniMax-01 performs effectively, especially on culturally specific queries, bridging academic performance and practical usage nicely. The discussion continues with creative writing and knowledge-based Q&A. The model can follow user intentions and provide detailed, accurate responses. It does well in summarizing and translating long texts. There are still gaps in more challenging instruction tasks, partially due to limited specialized data. The team plans to add more targeted training content. In user tests, the model uses search tools to handle knowledge gaps, focusing on precision and staying up to date. Careful dataset curation and reward modeling make this seamless. Now we pivot to MiniMax-VL01, which extends MiniMax-Text-01 to vision tasks. They add an image encoder and an adapter, and then train on a broad visual text dataset. They compiled 694 million image caption pairs and refined 180 million of those captions for high quality. They also built a set of 100 million images with human-refined descriptions averaging 300 tokens each. On top of that, an instruction set teaches the model to handle tasks like localization or problem-solving from images. These instructions cover a range of linguistic styles, preparing the model for multimodal challenges. Here, we see more details on how MiniMax-VL01's data is organized. They start with 1 million image instruction pairs, tagging them according to major visual tasks, like object detection or text comprehension. The dataset includes 50,000 unique tags grouped into big categories. The architecture is basically Vision Transformer plus NLP plus language model. The visual encoder has 300 million parameters. An image adapter then feeds into MiniMax-Text-1. Images are resized on the fly, split into patches, and sometimes turned into thumbnails to preserve small details. This multi-scale approach avoids the losses that come with heavy downsampling, which is helpful for complex visual tasks. They detail the multi-stage training approach for MiniMax-VL01. The first stage focuses on aligning visual and text representations, using large-scale image caption pairs, around 37 billion pairs initially, and 1.2 billion for fine-tuning. Contrastive learning aligns images with captions. Then they deepen visual comprehension by adding in text instruction data. Next, they incorporate real-world conversations to make the model more interactive. Finally, they refine preferences, using techniques that improve both response accuracy and user engagement. Altogether, these steps let the model handle a wide range of vision language tasks. The next part describes the multi-stage training and benchmarks. They generate diverse response samples, assign each a quality score, and then form high-quality versus low-quality pairs. Early stopping is used to avoid overfitting while refining preferences. They also keep mixing in purely text-based data to maintain a balanced grasp of language. The model performs well in visual reasoning and knowledge tasks, although it lags slightly in advanced math tasks. Evaluations of MiniMax-VL01 come from two main sources. The first is the MegaBench, which offers a broad spectrum of real-world tasks. MiniMax-VL01 handles knowledge retrieval and visual question answering effectively, though it finds advanced planning tasks challenging. It still compares well to many open-source vision language models. The second is an internal user experience benchmark that tests image annotation, instruction following, and more realistic scenarios. Results suggest MiniMax-VL01 works smoothly, especially for tasks in Chinese. In conclusion, the authors note that MiniMax models handle contexts up to 4 million tokens, which is a significant step forward. Finally, the paper discusses broader takeaways and current limitations. They've shown how to push long context processing much further with efficient attention. That unlocks possibilities for large-scale AI tasks. Still, the community needs better benchmarks for truly complex long-context challenges, not just simpler tasks. Some aspects of the architecture still rely on traditional attention ideas, and they want to explore even more efficient designs for larger inputs. Another limitation is programming performance, which could improve with more specialized training data. Despite these constraints, the MiniMax models are open source, so collaboration can drive more progress. And that wraps up the discussion on MiniMax-01, scaling foundation models with lightning attention. And that wraps up our deep dive today. It's been a long deep dive, but what a journey. From lightning attention to hybrid architectures, MOE, and more, we've covered a lot of ground. Thanks for sticking with me through all the details. Now go stretch a bit. See you tomorrow.